So today will be a shorter lecture, and you will not get any assignments for this task here. So this is something you can use if you're using in your projects, but it's really hard to get too many things that can go wrong. So I don't want to put an assignment here for this, but I will go through it. So the idea is that tell you about how you can integrate Python with Fortran with Python in a very easy way. And it's become more and more important to if you have computational codes and you want to kind of make them more accessible, or you want to accelerate your Python code, you can very easily interface it with Fortran. So integrating with Fortran with Python is you can do it in multiple ways, and the hard way is that you define your interface in C, because Python uses a C API to define extensions. And you express your extension by implementing a number of functions and compiling that together to a module. And that result of the shared library that you produce from this can be used like any other Python module. So it's when you do this, you will use it just like a normal module. So in this case here, this is just a C implementation here of a sum function. So you can see here that you use a Py object here. That is the kind of default object in Python. So if you start, everything in Python is derived from this, and that is actually a C thing. And you can see here that you have Py objects args. So everything goes into an object. And then you can implement your function here. The first thing you do is that you parse the input variables here using some complicated function here. And then you do your computation here in C. And here is where you can integrate your Fortran code. So here you will compile your Fortran code and link together and call it from C. And then you return your values here back to the Python interpreter. And then you do some other complicated stuff here to expose your interface to the Python interpreter in this shared library. You init module, and so on. This is too complicated. So there is actually a much easier way to do this, and that is called F2Py. And it's what it is. It sounds like, so F is Fortran and to Py, Py. So it translates your Fortran code automatically, looks at your input variables, generates the wrapper code required to interface your Fortran code automatically. And also when you install NumPy, this tool kind of comes along. So it's integrated with the NumPy library. It's a command line tool, so it's there is no easy way of using it. You need to type something on the command line to do it. You can do it also from your source code, so you can in your source code actually tell it to compile itself and create a module. So we start simple. So in this case here, we are going to expose a single subroutine here. This is the simple ABC. And what it does is just adds two variables together and returns C here. So you can see here I used intent in and intent out attributes, which are part of the Fortran standard. So they're nothing special, but F2Py reads those and does things differently depending if it's an intent in or intent out. So I'm going to use Visual Studio Code in this case here because I couldn't make it to work in the notebook. I'm going to switch over here. So you can see here I have my simple F90 here. And then I can compile a module. Let's see if I can. I do F2Py. -m here is the name of the module you want to create. So in this case, I call it simple. And then I do C to define which source code to compile. In this case, simple.f90. And I press enter here. And you can see here that it builds a wrapper here. And then it calls the build system here, it calls a Fortran compiler, does a lot of things. This is different depending on. So on Linux it looks a certain way. On Mac it looks something else. And you can see here below that it created something called simple CP13 win AMD 64.pyd. On a Linux machine, it will probably be .so, or same thing on a Mac. So in Windows, it's called a PyD to determine that it's a shared library. So in Windows terms, this is a DLL file. Then I can call my subroutine here. So in this case here, I will skip simple. Okay, I will do it differently. I see that I call it fort mod. It's fort mod. So now I have a fort mod module. You can also do it. I have created a special module here that helps you compile it internal. So you can do it from source code here as well. So in this case here, I can do F to compile fort mod and add the source code files here as well. So the first thing we're going to do is just kind of look at the documentation. So I'm going to do this manually here now. So I'm going to do Python. And then I do import from fort mod import star. So what now happened is that I have loaded in the DLL file, and then I can do print simple.doc. You can see here that F2Py also generates documentation. So you can list how you should call this function here by printing the __doc__. That contains the documentation. You can also do that on, if you do import fort mod like this, you can do print fort mod.doc. Now you can see here that this module fort mod is an auto-generated F2Py, and it contains the function simple.a. So if you have multiple functions, you get more of these in this. I can of course call this, so C equals to simple 2,2. So now you see those two arguments now went to the Fortran subroutine, and which calculated, and you return. I got back the 4.0 here. So fairly simple. You can also do a bit more complicated stuff. So let's see here. So let's see if we can do a matrix multiply. So here I have, now I need to be more explicit when I declare my things. So I need to provide the sizes of things here. So RS is the rows of A, columns of A, and then I have B, T, and C. So you can see I use these other parameters to declare the other stuff here. I still use the in-out to declare what I'm going to pass in and out. Then I call C mathmul here to do the matrix multiplication in Fortran. And then I compile this here as well. Now we need to think about things when we are going to use NumPy now. And NumPy is a C library. And by default, the arrays in NumPy are row-wise. And we need to use column-wise when we use Fortran. And we can do that by specifying order equals to F here. This will create an array with Fortran ordering. And when we pass that over to the module, it will be passed by reference. If we don't do it, it will still work, but NumPy, or the wrapper, will handle that by doing a copy. So it will kind of make sure that it works, even if you don't have the correct ordering. But if you do this, you will have more performance. Then we do C equals to matrix multiply A comma B, and we just do some checks here to see what actually happened. So we run this. Now you can see here I have built in this, it compiles the module when I run the code. Okay, sorry, wrong terminal. Let's do that. Why does it do like this? So you can see it builds the code. So now you can see if you start looking at, I print out the documentation here on matrix multiply. You can see here that I have parameters A and B. But now you can see a curious thing here. You can see here that it puts RST here with a bracket. And F2Py has figured out that these variables are just there for determining the sizes of the input arrays. And you don't have to specify them anymore. That will be automatically handled by the wrapper. Now you can see here the syntax is C here equals to something. And you have array floating point array with the bounds RS. And you have B here with bounds S comma T. And then you have returns the rank to array F floating point with R comma T. But you can see here that something here happens here. When we call here, C has actually changed. So it creates a new C array. So we actually are not even using this array here. And this can be problematic for efficiency reason. If you want to have an array that you have created in NumPy to be assigned by the Fortran code, we need to figure out something else here. So you can see that we have, it works like it should, but you can see here that these are not the same arrays. So how do we solve that? We go to the second Fortran example here. We don't have to change anything big about the code, but instead of saying that we have intent out of the C array, we say that we have an intent in and out. That means that when you compile a wrapper here, it will not return it on the left side. It will still be an input parameter to the Python code. So let's see here what we do here. Here now we call it like this instead. And we run the compiler here again. So if we look at the documentation now here, we have, it's almost the same, but it's now A, B, and C. And still we don't have to specify the R, S, and T parameters, but C is now still on the right side of the function here. And you can see it says in, out, rank 4, rank 2, we bounce R and T. So now you can see here that we can provide our C here, put it on as the last argument, and you can see here that the result will be stored in the same array here. So if you print C now, it's the same array as we call the routine with. So that's nice. Another thing you can do is also, so suppose you have a module, you can actually create a Python module that has a module internally inside it as well. So in this case, we have a matrix. Let's see here. We have two functions here: matrix multiply. That's the first one we did, and we have a second one here with an in-out statement here. So compiling that with f2py is very easy. So you do f2py minus m. And now the thing is that if you have modules that you compile into an extension module, you will have an under module. So you can have multiple modules in a single extension module, and they will have names underneath here. So I will do xmod here minus c matrix.f90. So let's do so I will do Python prompt here. So now I will try to import the module in two ways. So first I will do import. You can see here I have an xmod here now. So if I do xmod, worked. Then I do print xmod.doc. Now you can see here I have it says that there is in this extension module, I have another module called matrix. And that contains matrix multiply and matrix multiply 2. So usually when I have, if you want to have compile a lot of modules into a single one, I usually do this import instead, from xmod import star. That means that you don't get xmod in your namespace, you get only the modules that are inside the extension module directly in your namespace. So doing like that, then I can do print matrix.doc like this. And now I have my matrix module available directly as a Python module. I don't have this outer module here. Otherwise you get a really long hierarchy of modules if you want to do that. So I can do print matrix. I can go back now and do that one. You can see I have two functions here in my matrix module. So this is how you can compile modules. And actually modules is it will read module syntax automatically. The thing that you have to think about when you're using f2py is that sometimes you don't want to expose everything in your code. And it could be an idea that you have a special module that you compile with f2py that only exposes, so that's the only thing that it parses, and then you compile your other Fortran functions as a library and link them together. So that because otherwise for f2py will parse every single source code file you have, and it's not necessary that you want to expose every single Fortran file as f2py. And sometimes it can also be hard because f2py is not perfect, and it is not always it managed to compile to a module. So that can be a recommendation that you provide an interface. And if you're doing the particle system exercise, there will be you will create an interface module that you compile with f2py, and then you link the other modules as a library. So you have an interface part and you have a library part. Just to kind of illustrate how beneficial this can be, I have created an image processing example here. So in this case here, I have implemented a blur filter in pure Python. And now it could be that the Python implementation is not the best one. It uses NumPy and so on. I have implemented a blur filter in Fortran in a separate Fortran file, and I'm also using the OpenCV blur file just to compare how the speed looks like. So let's see here. This is the blur filter vectorize. So you give it an image, and this does its stuff here. I will try to make it as vectorized as possible in NumPy, but yeah, you can probably make it better. And then you return this here back. Then I have my Fortran code, which I've implemented in my filters module. And let's see if I can show that. Filters. So this is a blur filter in Fortran. So I'm implementing this in a module separately here, and then I have the image comes in here. The kernel size is also given, and then I have an output variable here with the filtered image. And you can see here I have the image here is intent in, and then I have the filtered images intent in out, so that we don't have a performance problem here. And then I do some stuff here. I actually use some OpenMP, and then I return my filter here. And then I also, let's see here, my image processing here. So to build that, I call this function here to compile it. I import it. I use the OpenCV here to read the image here. It reads it in grayscale for EC2. Probably we don't want to, in this example, we want to bother with the colors. I'm creating a Fortran array here. This is, I'm not going to time this, but to be able to pass it as efficiently as possible, I need to kind of copy it over to an image that is in Fortran order, because what I get back here from image read here is a NumPy array with C ordering. I set the kernel size to 7, and then I do, here you can see I do simple timing in Python. So I do start a timer, do my blur, and I call my time again here to kind of calculate the time it took in Python. Then I do the filtered image here, I create a 0 array. And then, because Fortran is much quicker than Python, to get a good estimate of the time, I run it 100 times. And then I do just an average of the time in Fortran. And then just to kind of compare to the most optimal way of doing it in CV2, which is the open the image processing library in Python, I use the blur function here, and then I compare that as well. So let's see if I can get this to run. So first it compiles the Fortran code. And this you only do once. So if you have already a Python module, you don't have to load that, do that compilation every time. It's one time. So you can see it took a single call to Python took 0.94 seconds. And then we have to do the 100 times for the Fortran code. So I'm running on batteries here now, so it's perhaps not the... I have gotten better numbers than this. So you can see here that when I run it on when it was connected to power, I got 0.0 or something on the Fortran, and I got half of that on the CV2 here. So I think this is related to that I'm running low powered here now. But usually you get the speed up at least 10 when you're doing this. So using Fortran can be a way of, just like you can do in MATLAB, you can compile your modules. You can write your critical code in Fortran and just link it as a module and then benefit from the performance. Or if you have a Fortran code and you want to provide a really nice Python interface to your Fortran code, this is also one way of doing it. Then the users can use Python to script your code. You can integrate it in workflows. So it's a really powerful tool to kind of integrate two languages and use the benefits of each. For example, if you don't want to do Python or a string manipulation in Fortran, you can do that directly in Python and then use Fortran for the computational parts, for example. Just going to see here so these are this is the unfiltered one. Okay, so they're just showing that you get the same image from each of them. So I didn't have so much